All right, so maybe while you guys are getting settled, uh, a couple of quick announcements. Homework 4 part 2 is due today at 5 p.m. No, sorry, part 1. Part 1 is due tonight at 5 p.m. and then the solutions will be posted immediately, and you can take a look at the solutions, of course. Any particular questions on that homework? I had a few people stop by my office about problem 3 in particular, which is good. And I saw that there's some hints posted in addition to the hints that I posted on discussion forums. So if you're still having trouble with part or problem 3 on homework 4, make sure you look at that. I think that should simplify quite a bit. And other than that, another announcement, I'm traveling on Monday and Tuesday, so I won't be holding office hours on Tuesday, but Monday's lecture would be taken up by Dr. Liu once again, doing some examples on the virtual work method and the Castigliano's theorem, probably including shear, axial, and torsion type of examples, which you can expect to see on the quiz 2, which will be next week on Friday, right? Yep, Castigliano's for trusses will be on that quiz, not for frames. So everything that we have covered up until homework 4 is on the quiz 2. Okay. Any particular questions before we jump into the lecture today? No?
Question like number 3 for the homework quiz.
Say it again.
Will there be a question like number 3 on the homework quiz?
You can expect bending, torsion, axial type of questions on the quiz.
3D?
Yeah, I mean torsion by definition is 3D, so
Oh,
it has to be 3D. But yeah, I think I'm sure whatever questions that we give or I give you, you'll be able to solve it if you've done your homework and looked at the books and the notes. Okay. All right, so let's get into the lecture for today. We're basically just going to continue on the handout that I gave you, I think, last time or the time before last time, which is basically covering Castigliano's theorems for beams and frames. So before this, I had already introduced Castigliano's theorem for trusses, which basically I explained to you the concept of the Castigliano's theorem. The concept entirely relies upon real energy. There is no virtual load, there is no virtual bending moment, and so on. So everything here for Castigliano's theorems relies upon real work done and real internal energy stored. But what we are really doing is we are taking the derivative of that internal energy stored, dUi, with respect to some additional load pi that is applied. And that dUi versus dP ends up being the displacement according to Castigliano's second theorem. And similarly, if you want to find the rotation at some point, you apply an additional moment at that point and take the derivative of the internal energy with respect to that additional moment. So I was telling you, I think in a nutshell, what that means really is that if I have some structure, a cantilever beam like this, there are some real loads applied onto it. So if you want to find the displacement at some point of the beam, then what you do is you apply an additional load at that point in the same direction. And you try to measure what happens when I change that load, the magnitude of that load, what happens when I change the magnitude of that load. How does the internal energy in the structure change when I change that pi? Similarly, if I want to find the moment or the rotation at some end, at the right end here, I apply additional moment mi here. And I see what happens when I change that moment, how does the internal energy of the structure change? And that happens to be, not happens to be, but it can be shown that that change in internal energy with respect to the additional load pi or change in internal energy with respect to the additional moment mi is equal to the displacement or the rotation at those points. Okay. So conceptually, it is very different from the principle of virtual work. In the virtual work, we were applying virtual forces, measuring virtual work, and we were talking about those yellow rectangles. Those were that's why there was no factor of half there. Those yellow rectangles used to be the virtual work done and so on. Here, there is no yellow or virtual work. Everything is green triangles, and the rate of change of those green triangles is what we are talking about. All right. So last time we had gone through this logic of internal energy stored in a beam is equal to half times the moment times the curvature and integrated over the length of the beam. And alternate expressions for that, those two we had also derived just by using m equal or curvature is equal to m over ei. And to derive to derive an expression for displacement, we said we'll need to take the derivative of internal energy with respect to P. And we went through this exercise of showing how we end up with expression that is extremely similar to the virtual work method. So in this case, what we are getting here is that the displacement at some point I is equal to the rate of change of bending moment as a function of P, when rate of change of bending moment as I change the load P times m over ei. So the idea is that you apply a pi here, you find what is the bending moment due to this pi, and when I change the magnitude of this pi, the bending moment in the beam changes, and the rate of change of that bending moment is this term m over dm over dp. And so last time I showed you that this term really is exactly the same as m prime over p prime that comes from the virtual work method. And this term, of course, is the actual curvature. So this is the rate of change of additional loads. This is the actual curvature. And similarly for rotation, if you were to write the similar expression for rotation, to find theta I, we'll have, once again, half times 2m as a function of mi now, right? So we are talking about this mi. If I want to find the rotation at the right end, I apply an additional load mi, and I want to find out how does the internal energy change when I change mi. So I'm going to just take the derivative of this expression with respect to this mi. Okay. So I'll keep the integral as it is, 0 to L. Half remains as it is. Derivative of m square is 2m, which happens to be, which will be a function of mi. Ei, assuming it remains constant with, well, it doesn't depend upon mi anyway. So then what else would we need here? I'm just taking the chain rule. I'm just applying the chain rule to take derivatives of this expression with respect to mi. So what would be the next term I get? Partial of m with respect to mi, right? Partial of m with respect to mi, and I need to evaluate that derivative at mi equal to 0. Just like I evaluate the derivative of this guy at pi equal to 0, this has to be mi equal to 0. So this is another point that I want to make sure is clear. Why do we evaluate the derivative at pi equal to 0 or mi equal to 0? Yep, go ahead, Drew.
That's like the point where like all of the real forces that you have, that's the deflection.
That's right. So when pi is 0, the structure goes back to what the actual real forces are applied on the structure, right? If pi is some constant value, then I have actually added on an additional load in addition to whatever the real forces were. And same thing for the moment. So we do want the derivative of the changing or the energy. So we want the rate of change of energy, but we want to measure the rate of change of energy at the point where the additional load that we applied is 0. Okay. So indeed, that's why it is That's why we enforce this mi equal to 0. And other than that, what we have here is just dx. And once again, you can see that this term right here, I'll write that in red. That derivative term is partial m rate of change of bending moment when I change mi at mi equal to 0. And the actual curvature, which would be d theta by dx. So let me just write it as m over ei, and the 2's cancel off. So that's m over ei. We have the integral 0 to L dx. This is extremely similar to the expression that we had from the principle of virtual work. This was m divided by m prime. Sorry, m prime divided by, I shouldn't write it as m prime divided by m prime, but small m prime is the term I think I used back in the virtual work method. So the bending moment due to the virtual load divided by the addition, the virtual moment I apply m prime, and this guy was the real curvature d theta dx. So once again, if you carry out the calculations, they are exactly the same as virtual work method, but in order to calculate these derivatives, you have to take a different approach to get to those calculations, and we'll see that in a bit. So this particular problem, for example, simply supported beam, load in the middle. This is a problem that we've done with the virtual work method also. Here, the problem that we are doing or trying to solve is what is the rotation at one of the ends. So in order to do that, we'd have to first solve the actual system. And let me write that here. This is the actual system. I'm deliberately not calling it real and virtual because there is no virtual in this case. It's actual and additional. So this is actual system. In this case, we would get a bending moment diagram that looks like this. P over 2 would be the reactions at the end, and that would be the bending moment diagram. The additional load is this guy. Sorry, the additional load is not this P. It's this moment M, because I want the rotation at that point. So the additional load at that point is this M. And what would be the reactions under this? Okay, M over L and minus M over L. So pointing up this way, M over L, pointing down, M over L. Those are indeed the reactions. What would the bending moment diagram look like? A straight line going from 0 at this point up to the value of M at that point, right? And that would be a positive bending moment. So something like this. And the equation for that would just be M over L times X. Right? So in order to calculate this theta rotation, I would need integral from 0 to L of partial M partial Mi. Actually, I should call this Mi. This is the additional load that I'm applying, Mi. So all of these moment and these reactions and this bending moment, I'm expressing it in terms of Mi, and this derivative is what I need here times the real moment divided, or the actual moment divided by Ei and dx. So can I do that in one shot? Can I double it up? No, right? Because these two things are, the additional load is not symmetric. So I would need to break it up from 0 to L over 2. Derivative of M with respect to Mi, what would that be? X over L. Yep. So since the bending moment here is Mi times X over L, if I take the derivative of this thing with respect to Mi, I get X over L. So indeed, that's X over L. And the curvature is, the real curvature would be P over 2X over EI dx. And the second term would be L divided by 2 to L. In that case, once again, the derivative of the additional bending moment with respect to Mi is X over L, and the real curvature is P over 2 times L minus X divided by EI and dx. And you can verify those integrals will come out exactly like what's written here below. We can verify the first one, P over 2 LEI comes out constant. What we are left with is x square. X square integral would be x cube over 3, and x cube is really just L over 2 cube. So similarly, all the other integral terms are written out here, and you get the same answer that you would get with virtual work or any other method, moment area theorems or anything. So critical things here for the Castigliano's theorem is that you draw the real, or say again, actual system with the actual loads, find out the bending moment, shear force, axial force diagrams, and then if you want the displacement or rotation at some point, you apply a load or a moment at that point. And that's the additional system. So you solve the additional system, draw the bending moment, shear force, axial force diagrams for that additional system, and I should write that critical step here. Taking the derivatives of this, partial m partial mi is equal to x over L. That x over L is what we are using in the expression for displacement and rotation. Okay. Any question on any of these steps? No. All right. Let's take well, we'll take an example in a little bit, but let me talk a little bit about other applications of the Castigliano's method. Just like the virtual work method, as long as you can calculate the internal energy stored in a system, you can apply the Castigliano's second theorem as well. So you can apply it to problems that have shear, axial, torsion, just like the virtual work method. And to calculate those energies, we've already seen you just add up all the different internal energies in the different modes. So the expressions for shear, they also look very similar. We have half times V over A, that's the stress, shear stress, times V over GA, that's the shear strain. Kappa was the shape factor. One of these A's cancel off. And what we get then is V square over GA, half is the factor, and dx. Okay. So if I want to calculate the displacement due to shear effects, then once again, to do that, I would need to take derivative of internal energy with respect to the applied load. And what we would do is partial ui partial p would be equal to, I can take the partial derivative inside the integral. Half is just a constant. We have v square, so the derivative of that v square would be 2v. All right, that 2v divided by a and g remains as it is, and I have partial v partial pi evaluated at pi equal to 0 times kappa dx. And of course, one of those half and 2 cancel off. And what we get is an expression that should look familiar from the virtual work method. It is the rate of change of shear due to additional load pi evaluated at pi equal to 0 and times the shear strain V over GA, and kappa is the factor times dx. Okay, and once again you should be able to see that this is extremely similar to what we had back then, V prime over P prime, right? Similarly for theta, we had derivative of u with respect to mi. That turns out to be integral 0 to L. Partial V partial mi evaluated at mi equal to 0, and the shear strain V over GA times kappa dx. That would be the rotation at some point due to the additional moment mi. So all the machinery that we had developed for real work, real energy, virtual work, virtual energy, being able to calculate UI, bending, shear, and axial, that's still all perfectly valid. Okay, and the other expressions I've already listed out here. I don't want to derive them again, but essentially deriving them means taking the derivative of expression like that, 2 and 2 cancel off, and what you're left with is this derivative and the shear strain. So in this case, maybe I'll write that here. If I take partial ui partial pi, I get integral 0 to L half times 2 n over ae partial n partial pi evaluated at pi equal to 0 and dx. Once again, this 2 and 2 cancel off, and what we get here is this expression right here. Okay, same thing for the torsion. Partial ui partial pi is equal to integral 0 to L half times 2t partial t partial pi evaluated at pi equal to 0 and dx, and denominator would be gj. So if I simplify that, once again I get this expression. So no matter how complicated a problem looks, as long as you can calculate internal energy, and as long as you can take derivative of that internal energy with respect to the additional applied load P or additional applied moment M, you can solve that. Okay. I think this might be a good point to take an example. So we'll do this example together, and then the next example would be something that I'll give you as an in-class assignment, which would be basically taking into account the shear and axial and bending effects. So in this first example, is this example on your handout, by the way? Yes. Okay. The next one might not be, but okay. So we have a frame. Hopefully this frame also looks familiar. Has this been one of our homework problems? So this frame with 5 kip per feet distributed load on the vertical leg, and there's a roller on the right hand side. So the deflected shape, hopefully you all remember, the vertical leg pretty much behaves like a simply supported beam, and since that angle has to be 90 degrees, that deflected shape pretty much looks like this. The horizontal member remains straight, and just like before, we are trying to find the horizontal displacement of B. But if you remember from this homework problem, there was no horizontal displacement at B. Why was that? long back when we were talking about this, we said horizontal displacement at B would be 0. Anybody remember why we said that? Because we were not taking into account the axial and the shear deformations. We were neglecting axial and shear deformations. We were taking into account only the bending deformations. But now we are going to take into account bending, shear, and axial, everything. So this horizontal displacement will be due to, pretty much only due to, the compression of this leg BC. Okay, and it's just as a matter of clarification, it might look like that this member, horizontal member, tilts, and due to this tilting, there would be a decrease, that this node might tend to move right, and that's a correct logic, but that's a second order effect. It's a second order effect which in linear elastic problems we neglect that second order effect. Okay. All right, so the real or the actual part of the system once again has been already solved for you. This actual system, we can see first of all, since this guy behaves like a simply supported beam, the bending moment here is just quadratic. The shear force go up by 25, go linearly down to minus 25, and the axial force is just in the horizontal member, right? So those real axial force, shear force, and bending moment diagrams, I hope, make sense. There is indeed no bending moment in the horizontal member. That's why it remains straight. And then now let's take a look at the additional. So I'll call that additional load. So to find delta B, what should be the additional load that I apply? P at that point, right? I want the horizontal displacement at B. So I'll apply P at that point, or I should actually say Pi at that point. That Pi will be immediately resisted up by this Pi, and pretty much everything else would be 0. So what would the shear force, bending moment, and axial force diagrams look like? What would be the axial force diagram for this additional system? Only compression in this member, right? And compression is positive or negative? Negative. So we'll do that minus minus excuse me, minus Pi here, 0 shear force, 0 bending moment. And what should I do next? Now that I have this additional system, the response of the, I have the response of the real system, I have the response of the additional system. What should I do now? Go ahead. Yes, we do need to take derivative, right? Partial of n with respect to Pi. There's nothing else here. So just like in the example that I showed you with this guy, we do the real or the actual system, we do the additional system, and then we take the derivative of the bending moment diagram or the shear force or the axial force diagram. So that's what we'll do here. Once I find once I find n, I'll find dn dp. That of course is just minus 1 in the horizontal leg, 0 everywhere else, and that's the only thing that is non-zero. So for delta b, I'll have 0 to, I think I'll just keep it as L. I have, and I should really draw that in red. So that's in red, except the frame. So partial n partial Pi evaluated at Pi equal to 0. Since this is a constant at Pi equal to 0, it's the same constant, minus 1. And I have n divided by AE and dx, which should equal to 0 to, I'll start substituting the values, 10 feet, 0 to 10. The derivative is -1, and the real force here is -25 kips. So I'll write that as -25 over AE dx, and if I integrate that, I get 250 over AE. The units, kip feet divided by AE, so that would cancel off and it will give me something in feet. Okay, so as we had anticipated, the horizontal displacement at B is pretty much only due to the compression of this horizontal leg BC, right? For delta C, the second part, for delta C, I in this particular case it happens to be equal to delta B, but so you could apply a moment at delta at B or at C, but just to be consistent, we'll go ahead and do that also. So apply a moment at C. That's third part, I think. Yeah, for delta C, the additional load is MI out here. Under the action of this MI, what would be the reactions? What would be the reactions for this? So would it be vertical or something else? Horizontal, because this guy cannot provide any vertical force, right? So it would be horizontal in the amount MI divided by 10, which is the length. So opposing the moment MI divided by 10, and this way MI divided by 10, and there won't be anything else. So which means that this horizontal member would be in tension, a constant tension of MI over 10. That's positive, so I'll write that as MI over 10. There's no axial force in this guy, the vertical member. There's no axial force there, 0 throughout. So shear force, if I take a section at this point, then shear force would be positive MI over 10 at this point, and it will be constant through the vertical leg. So positive MI over 10, and there is no shear force in the horizontal member. So like that. How about bending moment? Right, so bending moment would be 0 here. It would increase linearly to MI and then stay constant here. Make sense? Right. So in any case, you can draw the free body diagram of this leg and see what that happens to be. So this would be like that, and MI. If I measure this x1 from the bottom, then this would be MIX over 10, and this guy is a constant MI. So I have now the additional, or the response of the additional system as well. So what should I do next? Take derivatives. So derivative of n with respect to MI in this case is 1 over 10. Derivative of V with respect to MI is again 1 over 10. And derivative of M with respect to mi for the vertical member is x over 10, and derivative of m with respect to mi for the horizontal member is just 1, right? And once I have that, then I can go ahead and do my integrals. Integral 0 to 10 of the axial component, which would be 1 over 10 times the real axial component, which is minus 25. So minus 25 over AE dx, that's the axial part, plus integral 0 to 10 of the shear force in the vertical leg. So that's once again 1 over 10 times the virtual or the real shear strain. That would be 25 minus 5x1. So that's 25 minus 5x1 divided by GA, and we'll include that kappa factor and dx. And that's the shear part. And finally, the bending would be, we need two integrals for bending, so 0 to 10. Let's do the vertical first. That bending moment or rate of change of bending moment is x over 10, and the real bending moment there is 25x minus 5 over 2x squared. Maybe I'll write it as 1. So 25x1 minus 5 over 2x1 squared divided by EI dx. And the second leg would be again integral 0 to 10, the horizontal member, that's derivative is 1, and the bending moment, real bending moment there is 0, so that's really does not contribute. And that third integral is bending. Okay, and let's check. And I'm sure you can evaluate these integrals, but essentially that's how you would apply the second Castigliano's theorem to solve problems in beam or frame type problems. So again, the critical steps are, given the real or the actual loads, find the response of the actual system. And if you want to find the displacement or rotation at some point, go ahead and apply an additional force or additional moment at that point, calculate the response of the additional system, and just calculate the derivatives of the response and use the second theorem of Castigliano. Okay. All right, so I think this might be a good point to do this example. This actually is an example from your book. In the book, it's an example for the virtual work method. Instead of using the virtual work method, we are just going to use Castigliano's second theorem. So once again, we are given a frame. We have this pin joint at A, and we have a roller or horizontal roller at C. And I've already solved the real system or the actual system for you. And the problem says find the horizontal displacement at point C under these loads. So take maybe 3 or 4 minutes, try to solve it by yourself. Again, don't need to crunch the numbers. You just need to set up the integrals. I'm sure you can crunch the numbers if you have given more time, right? So just set up the integrals, and that's what I would like to see.
Horizontal displacement